don't know if you have the context. As a kid, I grew up a 40-minute bus ride to New York City. In an hour, we could walk to a Broadway show. We could get on a bus and you know, a couple blocks over, you're on Broadway. And you go on a Wednesday or on a Saturday afternoon and you can get discounted tickets, if they were trying to fill the thing. And we did that. That's what we did after the prom. Most people went down to the beach, which is the New Jersey beaches, which are close at hand. And my buddy and I and our two girls went. We had lunch and went to a Broadway show. Instead, which was pretty cool. Nevertheless, so let us be okay. We're going to pick up where we left off in the wonderful realm of muscles, and to me, we really are starting to get in. This is really, again, this is the more rigorous material I think that we face throughout this particular course. And you might remember this is the last thing that we saw here. We're looking at these myofibrils. And I mean, so think of them as just flexible rods that fill every single muscle cell and every single muscle mass. Thousands of them, as you can say. A tremendous amount of the volume is protein, protein, protein. There's a certain amount of fatty tissue. There's a certain amount of glycogen. There's a certain amount of myoglobin, and those are certainly, myoglobin is another protein. But they are tremendously filled with these protein filaments. And because of the banding that you will see today, they become striated. We look at it because it's just a series, and we see this tremendous amount throughout our studies in this term, repeat units. So if we analyze the individual unit, be it a cell, or in this case, a portion of a cell, called the sarcomere, then we really get an idea of what's going on. So here we are. This is the individual cell, okay? And what they call, again, muscle fiber and cell are interchangeable terms. You can see the alternating banding pattern here between light and dark bands. And again, you'll see in the dark bands is where they overlap. You can see the abundance of mitochondria. You can see the abundance of the rods that are there. And as you can see, that we'll name these bands A bands and I bands. It stands for anisotropic and inotropic, which is hard to remember, okay? Having to do with light planes and things like that. It's sort of like, right and left-handed forms and all that's different chemistry. They're not interchangeable, but nevertheless, here's how I remember it, and it works. Dark has an A and light has an I. You can't possibly get the question wrong. It's like there's no I in team, but there's an I in light.
That's actually.
But
that will help me out.
Hey, I got all that. I got skills, baby.
So can we talk about the fact that one of the recordings for the exam last semester, you literally put in it, if you get this question wrong, I will kill you.
Did I say that?
You did. I recorded it. It was funny.
Well, at least it wasn't that controversial. I haven't been reported. We'll know soon. My contract is up for renewal. We'll see if they want me back.
Oh my God, that's so sad.
If they don't, all I can say is, hello, Florida. I'll be laughing at you, sunning in Florida. And I for light band. So the stripes form this repeating band. A are the dark because they overlap. As you will see in the middle of the A band, there is an area where there isn't an overlap effectively permitted. It will be obscured when the muscle contracts. But they call it the H zone because it resembles a letter H. And there's a line of proteins, got a fancy name, myomycin, which you don't have to know, that vertically, it has to do with the attachment of the myosin microfilaments that you will see shortly. The I band is standalone, basically actin filaments not overlapping the myosin. And because they zigzag, these proteins, they've called it the Z disc, and that is the boundary of individual sarcomeres. They go from Z disc to Z disc, and I may have said this to you before, as I like to say, from Z to shining Z. Remember America the Beautiful? We did all that. Oh, yeah. Do they still do that in high school? We did, the whole pledge thing, and we used to do the Bible readings, which They were very. I figured I used to do it, and I did every single song. Edited for Jewish people. I'm not going to do that humor. It's going to be controversial. This is what it looks like with the bands. The sarcomere contains on either side an A band because you're going to see the actin filaments are effectively attached to the Z discs that are there. So they have a half on each side, and that's what they classify it. And there's an entire A band. All within every sarcomere is a unique set or an identical set for every sarcomere of myosin. So, and again, they use the box, whatever analogy you want, because effectively, if we see what happens in one unit, it just repeats itself. So if you watch how one contracts, they all contract, and they don't contract. This is just basically shortening. It's the walls closing in. It's a sci-fi film, It's basically what happens. Indiana Jones, Temple of Doom, not Temple Bethel. That's a line from Spaceballs. It's a Temple of Doom. Well, it's the late Joan Rivers. It's not Temple Bethel. Here it is. So the H zone in the middle, typically when you look at these at rest, and you'll see the actual micrographs. This is the schematic. The red are the myosin. The blue are the actin. Okay, so they are structural in nature, and by definition, they are motor proteins. Motor because they undergo certain kinds of shape changes that facilitate movement. So it's rather that, anytime it changes shape and induces something to move, we refer to them as motor proteins. And so in blue, on the edges, you can see the Z disc. So we focus on one sarcomere. So it's very orderly in nature. The actin are thin. They are little globules of actin, which makes microfilaments in the typical cell with cellular anatomy. But when they strand together, they become fibers, but they can assemble and disassemble. In muscle, they don't do that. In muscle, they stay assembled. And they're anchored to the Z discs on either side of the boundary. The myosin are thick, and they have an interesting shape. They're intertwined, as a lot of these are. The actin filaments is just like a strand of pearls that you twisted. So it looks like a double strand of pearls that someone might wear as a necklace. It's there. But when you look at the myosin, and you will see it, you can see it has heavy chains and light chains, and the heavy chains are effectively braided, and then the light chains are the ones that facilitate the motion that occurs. And they are connected at that mid or med line, and their M line is sufficient. And what's interesting is the hexagonal arrangement. And so you see that, and it's a very good illustration pointed out. So roughly it's 1 to 2. Some authors have said 1 to 3. You have, because we look at everything two-dimensionally, but when muscle contracts, it contracts three-dimensionally. Okay, so why do things bulge in the middle? It has to do with the arrangement of all the fibers. When you think of somebody flexing a biceps brachii. So you have a myosin. So rather than just being in this sort of flat fashion, you can see this hexagonal arrangement. So it's hexagonal, and yet there's another hexagon adjacent to it. So when they come closer together, they don't just slide this way, they're coming close together this way. Now the bulge comes from the arrangement of the fascicles themselves, and the nature of that muscle. Typically, when you see ones like the biceps brachii, we call it fusiform, it's got a belly. And when it all kind of comes toward the middle, it expands. It expands in multiple directions. So in the I band, all you see are the actin filaments. In the H zone, you don't see any overlap. The M line, you have these accessory proteins stabilizing it. And then you have the actual, when we start to look at the overlap area at the true A band, now you can see the overlap that's there. So thick filaments, the myosin, and they're interesting because they each have active sites. Those active sites, if they come in contact with each other, and they're very close to each other to start, they immediately will interact. And that's effectively how your muscle contracts. What precludes that, what governs that, is that the active sites, and again, we name things often for what they're going to attach to. So on actin, you have myosin, active myosin binding sites. On myosin, you have actin binding sites, not for what it's on, but what it's going to attach to. On the actin, those myosin binding sites are covered by a strand-like protein called tropomyosin. There's several of them, and they sort of swirl around, if you will. They sort of wind around and cover those heads. They are held into place by plug-like proteins called troponin. The troponin anchors them. And by anchoring them in place, they cover the binding sites that will go toward the myosin binding sites on the actin. When the troponin is altered, and this is the chain reaction, it's how a muscle contracts, calcium is released from storage areas within the muscle called terminal cisternae. It floods the interior intracellularly. And what happens, those calciums, when they attach to troponin, they change its shape. You can see a bunch of animations that show you how it happens. It effectively allows that tropomyosin to slide out of position, expose the binding sites, and they attach to one another. Once they attach, that head of myosin is in a cocked position. Muscle, when it's relaxed, is ready to contract. The idea of being relaxed means it's not contracted. It doesn't mean it's not able to contract. It's energy preloaded. And so once they attach, boom, it immediately, and we'll look at the reaction involving ATP and how it not only contracts, but also how ATP permits it to relax and effectively recocks the head. And as long as you have calcium present and obviously sufficient energy, it will keep doing that to such an extent that eventually it will go toward a point of maximum contraction. When you're doing a workout, when you're doing an exercise or an activity, whatever. Okay, so the thick filament, myosin, 2 heavy and 4 light polypeptide chains. Okay, the heavy chains are intertwined. Well, again, whenever you braid something, you impart strength. The light chains form that so-called globular head. The heads link thick and thin filaments. Cross-bridging is the phenomena. Myosins are offset, so they're not in alignment. It's not like you have a myosin head, exactly spaced. Effectively, this intertwirling of the fibers, you have a head here, so they're eccentrically placed. And the beauty of that is when they detach, imagine it's a spring-loaded system. It's an elastic system, as you will see. There's a protein called titin. And with that T-I-T-I-N, not A-N, how it is, it's not like Clash of the Titans or Last of the Titans. Pardon me?
Is it the largest protein body?
Titan? I don't think so. Size-wise, no, I wouldn't think so. I honestly don't know how to look that up. But very good movie, the 1981 version, Ray Harryhausen, the stop action effects. Maybe I've told you about that before. Originally, how they did monster movies like that was they would have a rubber model or a plastic model, and they'd move it a fraction of an inch, take a picture. It's called stop action photography. And it was the basis for things, famous ones. And that's how he did all those, and then they put them together. It's great. Harry Hamlin, Sir Laurence Olivier, Dame Maggie Smith in a role where she was like the bad guy goddess. Good-looking lady when she was young, not like down nappy. It's like I'm a stranger in a strange land. Moving on. So what you will see is, because they're eccentrically placed, if they all release simultaneously, it would spring back to its original position. About half of them stay attached, and half of them detach. And then when it ratchets, what I call it, when it continues to contract, then you have the side that wasn't attached is reattached, the side that was attached releases, and it can contract some more. And they do this pretty well in an animation that we will see, one of the 3 animations, which we do not think we will get to today, maybe the first one. Myosins are offset. staggering array, different positions. That's what I'm driving at. The thin filament starts with globular units, so it theoretically could assemble and deassemble, but when it's put together in a strand, it becomes fibers or F-actin. Okay, each of those individual actin units has a binding site, just like on the heads of the myosin, though named differently. And again, you'll see the configuration, and then you'll see what we call regulatory proteins because they govern the function, tropomyosin and troponin. So here's what it looks. This is an individual. I'm thinking Twizzler. I used to bring in peel apart Twizzlers and regular Twizzlers.
That's what Dr. Hammond did.
I don't blame her. And if you don't like the lecture, always leave the Twizzlers. So much licorice, so little time. And so here it is, a Twizzler, and here are the heads, there are the binding sites, and you can see how it is arranged. So this is a very large, comparatively speaking, molecule when you put the individual strands together. The thin filament, you see the double string of pearls configuration. You see the troponin, the plugs in yellow, the tropomyosin in that sort of orange or brownish color, and of course the binding sites. So they all form what we refer to as the myofibril. That's that flexible tube. Remember, the filaments are those individuals, actins and myosins. The elastic one, the tighten, thick filament in place, recoils, resists excessive stretching. Dystrophin. Now, usually when you see the prefix dys, like dysphagia, trouble eating, okay, it usually means an irregularity. That for whatever reason, I think they named the protein for the disease. Okay, and that's my take, because a lot of times we'll do that. Dystrophin links thin filaments to the proteins of the sarcolemma. Okay, so those are the actin filaments and the ones that are principally in and around the Z disc, etc. There are other proteins that are play there, and they maintain the alignment. Then they talk about it. I've heard it pronounced differently. I call it Duchenne. Okay, Duchenne's muscular dystrophy is, again, isn't this sex-linked recessive? You genetics people, yes. Okay, sex-linked recessive. So we see it mostly in males, as you probably know. And the way to appreciate it is because of whenever a structure is not being formed properly, it begins to deteriorate. So you see what appears to be muscle mass, but really it's not well-formed muscle, and it really becomes almost layered with fatty material. So you don't have the strength, and it's the old story. Eventually, respiratory becomes the area of concern, not just the dysfunctional. So it progresses from the extremities centrally, head, chest, cardiac. Those are the big players. And I think there's been a certain amount of improvement with regard to these things. I wonder if they're trying to treat this with some type of genetic gene therapy. I don't know. So the defective gene they have named for dystrophin and the stabilizing, etc., tears easily, damaging the fibers, inflammation, apoptosis, muscle mass, and again, it's typically replaced by deteriorated tissue. So it was a disease, and like many of these diseases, really had a very, very shortened lifespan. That with time and improvements in therapy and recognition has improved. Every year at Labor Day, there was a wonderful telethon by the late comedian named Jerry Lewis, who my uncle and he both dated the same girl at Week Lake High School, Newark, New Jersey. He won. He got famous and rich. 6 kids. Just saying. The cheerleader, and Jerry Lewis and my uncle Ed competed for her. Little nugget of information, in case you're wondering. He was born Joseph Levitch. And then a guy from around here. He grew right over the border of that wonderful triangular bridge into Ohio, whatever that is. What's over there? Go on 22 and you're heading to Ohio. You know where I'm going? Where Star Lake was, wherever that is, just past there's a bridge. Help me! What's the name of that town? That's
Starlink?
yeah, past it in Ohio.
Florence? Oh, in Ohio?
Yeah.
Steubenville?
Oh, it's Steubenville. Oh no, he's from Zanesville. Maybe he's from Steubenville. Dean Martin. The whirlwind of popularity. Okay, so that I need to show you a picture, etc., etc. Supportive care, and it's improved a lot. A lot of it was that telethon was interestingly started in a bowling alley across the highway from where I used to live. Just little nuggets. I was there. I was telling the students about Legionnaire's disease when we first identified it. Philadelphia, I was there. Old Bellevue Stratford Hotel. Still getting nasty letters saying I did it. See, I told my micro class, which is entry level people, I said we used to meet there because we had an honor society. I don't want to strain myself, patting myself on the back. Okay, sarcoplasmic reticulum. Okay, normally we're used to seeing sarcoplasmic. There's very little in the way of rough endoplasmic reticulum. It's nearly all smooth. And one of the roles of sarcoplasmic reticulum is to form cul-de-sac pockets that store things, in this case, particularly calcium. The calcium that affects skeletal muscles is intracellular, it's there. The calcium that has the greatest impact on cardiac and smooth muscle, particularly smooth muscle, is mostly extracellular. And that's when we get into smooth muscle, we'll be looking at calcium channel blockers, which many people, myself included, take for blood pressure and other related problems that are there. The sarcoplasmic reticulum underlies the sarcolemma, and it's intimately associated, as you will see, specifically structurally in areas at the juncture of the A and the I band, where they form an interesting structure called a triad. The triad is an extension of the sarcolemma, the plasma membrane, which fires, which alters significantly, triggering voltage-gated channels. Those voltage-gated channels, you're going to see juncture points on either side of that called terminal cisternae. Cistern is a well. That's one of the things that these cisterns are, these infolding cul-de-sacs of sarcoplasmic reticulum that contain calcium. When it goes through and that voltage-gated channel triggers a companion channel on the cistern that allows the calcium to be basically released into and diffused into very rapidly the skeletal muscle cell. So the terminal cisterns project perpendicular cross channels. It effectively it regulates the intracellular calcium, storing it, releasing it. It releases very quickly because of the voltage, which means that there's a lot of energy requirements. It requires energy to pump it back in. So when you use muscles, you use a lot of energy relatively quickly, comparatively speaking to other systems. The T tubules are the protrusions of the aforementioned sarcolemma, all about surface area. The lumen is continuous with the extracellular space. And so in that fashion, it allows the electrical nerve transmissions to reach deep into the interior of each muscle. And you have wonderful illustrations in these animations that demonstrate that to you. The tubules penetrate the cell's interior at the A and I band, and there's the triad that I talked about. Integral membrane proteins within that transverse tubule, that's within the extension of the sarcolemma, that are into that intermembrane space, okay? And again, voltage sensors or voltage-gated channels that alter shape with response to the changing electrical current, and that effectively controls other channels, which are effectively the combination of the voltage-gated channel and the calcium channel in the cistern, allowed for the calcium to come in. So as the impulse passes by, the shape change effectively releases the calcium. It's a very good illustration. So each one of these bundles, each one of these myofibrils, when we look at them here, they are enveloped, not just surrounded by membrane endoplasmic reticulum, but you can see how it surrounds each individual fibril, mitochondria, all over the place. In this sort of grayish color, you can see the extensions, which are the T or transverse tubules, and in blue, those widened areas. So there's a triad here and here. 3 structures together is how they're describing it. All of this serves to activate the sliding filament model of contraction in a phenomena called excitation, that voltage, the excitation, leading directly to contraction, coupling those, a wonderful energy transduction from electrical to mechanical energy. And because it cross bridges, they shorten, et cetera, et cetera. So typically when your muscles are relaxed, you'll see the illustrations and the actual micrographs. You're only going to see the overlap only slightly at the ends of the A band. Okay, so they slide past one another. They don't change length, they just change their relationship. So again, the whole idea is nervous system, voluntary. You're telling your muscle to contract or do something, and effectively the cross bridges form. Again, the more that you, whether you're just contracting a little, and that's the distinction between moving something just a little bit or doing something significantly vis-a-vis contraction, you're able to generate more motion, more power, more speed. Effectively, because the actin filaments are attached to the Z discs firmly, as they slide toward the midline and overlap more, effectively making that A band appear enlarged. Okay, effectively, the boundaries, the Z discs are coming closer together. So the Z discs become closer. The H zone disappears because that you only see that because there's no overlap, etc. So here we are, and you flip between the two. Here's relaxed. You can see that H or middle zone. You overlap the white and dark the Z discs. So if we focus on these Z discs and click, which you can do easy with this, right? Look what I got. So now I'll backwards it. So here I am here at a contracted. You can see now the A band doesn't appear as dark, but it's much more complete, and the I band certainly has shrunk. So if I back it up, look where it is now. So it's moved on either side, roughly from here to here, perhaps maximally shortened by about half on each side. So it's a pretty remarkable degree of contraction. And if we move it forward, you can see that's a lot. So that's what and you can see the tighten here. If we back it up, you can see how it's more stretched out, less coiled. You can see the relationships with the heads. You can see the midline area, etc. So effectively, that's the anatomical basis microscopically. Now we have to look at the events that bring this together. And the way this and a lot of texts do it, they divide it into 3 major areas, each with many steps. So maybe there's 20 or 25 steps total, which you guys unfortunately need to know. Starting from me telling my muscle to move, a voluntary thought that's going to be demonstrated by me, whether you're typing something, moving a keyboard, a mouse, whatever. Okay? Activated by the brain, the signal is transmitted, brain somewhere in the spinal cord, typically, let's say, or cranial nerve, and then out to wherever the location is of that muscle. And as you will see, the motor group that's there. So, because they're capable of changing resting membrane potential, the first thing is the first and most, truly the most abundant and the best studied of all of our neurotransmitters. Remember, it's an electrical system that basically executes the vast majority of its commands by way of releasing a chemical. My favorite analogy for showing how that works, my daughter, I give her credit because she told me about it, I don't know, 24 years ago. I said, this is how it works. She goes, and what I used to demonstrate, she goes, pixie sticks. Different colored pixie sticks with a little like powdered sugar, all that. And I hit it, and out came the stuff. Pixie sticks. So What happens that, so effectively, this particular sugar substance out of the pixie stick is the most abundant, and it's really a unique neurotransmitter by way of classification called acetyl or acetylcholine, depending on how you pronounce it, typically abbreviated that way. And it's an abundant substance we use in multiple areas. The acetyl group, as you guys all know from organic, means acetic acid, okay? So it's taking that. Did Dr. Badger use the term moiety? Yes. That two carbon unit, we used to call it a two carbon moiety, the acetyl group. Chemistry major, remember? 51 years ago or whatever. Don't start. And choline, which we use all over the place. Okay. So choline is an important ingredient when making lipoproteins and that type of stuff. So they're used substances. Ion channels. Okay. Two classes of ion channels. Ligand or chemically gated channels, those are the ones on the motor end plate that respond to the acetylcholine being effectively spit out or exocytosed by the motor nerve. And, not to be outdone, voltage gated channels for including calcium, sodium, and potassium, are all part of this construct. They open or close in response to voltage gated change. They show the typical illustration. There's the ligand. There's probably basically showing you sodium going in and potassium going out versus the voltage gated channel. And some voltage gated channels have that bad boy. That's really an important concept. That is an inactivation gate. It's normally we talk about open and close, but it's like that door. We can open and close it, but what happens if we lock it? Then it's not so easy to open it again, is it? That's the inactivation gate. It's a lock. Why do I mention it to you? Because down the road, we're going to start, particularly not so much here, because nerves and muscles, skeletal muscles fire rapidly, but the heart has a wonderful contract. The heart beats more rapidly than every second of your lifetime. It has a guaranteed roughly quarter of a second time off. Every time I beat, I get a quarter of a second break. That's the heart. That's how it works. So you're going to see those inactivation gates. That's their job. Motor nerves and the neuromuscular junction. So the first part we look at is the neuromuscular junction. All of the steps that effectively take us to creating the action potential. And terminology is important because in the next unit, when we do the nervous system, we have action potentials, but there's some nuances in terminology that are distinctive between the two. And since we look at the two very close time-wise to one another, it's important to remember the distinction. So these are somatic motor nerves, effectively meaning they go to muscles or joints or related body structures, voluntarily controlled. We know the axon is very, very long. It can be extremely long, perhaps even a meter long, depending on the location of the muscles, coming to the spinal cord from the brain or from the spinal cord down to the muscle. Okay? They divide, they branch out, and in their branching, where they contact, you're going to see these tiny bulb-like projections that attach is the wrong word, that are again, this is not a direct attachment. It's not like you plugged something in. Okay? The neurotransmitter is released and there is a space. We'll talk about this space all the time in nerves and muscle. The space, I always learn to call it a synapse. Most books will say it's the synaptic cleft. It's a finite space, extraordinarily small, but clearly a space because the end of the nerve and the motor end plate, the receptor, are not in direct contact. And ladies and gentlemen, that is the rate determining step. That is what occasions some muscles or some nerves to be faster or slower than one. That's how it works. How rapidly it comes across, what kind of contact point is it, how that neurotransmitter works, etc. What's going on with it. Each muscle fiber, each of those individual components, cells, has one neuromuscular junction with one motor neuron. Effectively, it's a branch. Remember, when we talk about a nerve, like if you're talking about the sciatic nerve going to your calf, first of all, the sciatic nerve is a mixture of two nerves, and each of those nerves have branches. So we're looking, and it's all composed, as you will see, of individual axons that are there. So we're looking at one individual axon, of which there's thousands in the nerve. And so this is what you're looking at. So here you have the neuromuscular junction where the motor neuron contacts the skeletal muscle. Again, contact, but not in a direct sense. Multiple axon terminals, and what they talk at what they call junctional folds. And you're going to see there's a lot of surface area, and it very much from a micrograph looks like this. So the synapse or synaptic cleft is a finite space filled with a gel. A lot goes on in there. Particularly when we get to the nervous system, that's where we therapeutically have the greatest impact. Medications and therapy, they mostly work in and around the synapse. We'll talk about that at length. So we start with the tip of the axon itself. The axon itself, just like any exocytosis phenomena, except this one is generated because of the impulse, fairly directly, you would say, contains, and each nerve contains at least one, and frequently more than one, kind of synaptic vesicle filled with a nerve. Most nerves have more than one. Skeletal nerves going to the muscle itself probably are just acetylcholine. The nerve going to the muscle, going from the brain to the spinal cord, has at least two. You have something that's going to tell the muscle to fire, and something that's going to tell the muscle not to fire. And that's really important stuff. Okay, as we move on. So these vesicles we'll refer to as acetylcholine. The infoldings of the sarcolemma on the individual cell, junctional folds, and you'll see they account for a lot of surface area, with that repeating idea of folding to increase surface area, with a ton of receptors. Those are ligand-gated channels. So the junction is the axon terminal, the cleft, and the folds. Voila. So here you have the vesicles. Here you have an abundance of mitochondria. Here, two-dimensionally speaking, you have the folded space. Here, you can see some degree of exocytosis, connecting to or attaching to very, very rapidly. There's just a tiny space. And opening that channel, and what you will see, sodium goes in, potassium goes out, 3 sodiums for every 2 potassiums. We've seen this movie before. Okay. And what it's going to do is it's going to make the interior more positive, or if you're like me, less negative. My wife hates me because I'm never in a bad mood. You're always so happy. I can't help it. I was peeved at the pooch last night. He knew he was going to daycare. He just was very excited. I want to go in, I want to go in. I want to go in, I want to go in. The big picture. Neuromuscular junction, we'll talk about that. First, we have to have the initiation of the nerve impulse. Excitation of the muscle, contraction, coupling. So these first two are coming together. Then excitation, contraction, coupling, then the cross bridge. As you can see, there's a lot of stuff going on here. That's the difficulty. So it starts right away. Sequence of events. A motor nerve fire. I'm going to move my muscle. Down its axon. before it releases the acetylcholine, there's a first step they don't even mention in here. Right there. At the end of the bulb of the axon, at the terminus, there are voltage-gated calcium channels. This whole event starts with voltage-gated calcium channels and effectively concludes with voltage-gated calcium channels. So what does the calcium do? The nerve fires, calcium comes extracellularly in this case. And again, I'm making a distinction between extra and intracellular calcium. Calcium levels are very important. You have different things that work on intracellular, extracellular calcium. Comes down, the impulse comes down here, opens, the calcium floods the terminus. What does it do? It facilitates, it encourages, and it creates the union of those aforementioned T snares and B snares to allow for exercise. This is where the Botox works. Okay. Botox works specifically at the neuromuscular junction of skeletal muscle. We use it in other areas, okay? And I think there's some activity, but my understanding, most of the activity is from there, okay? So the motor nerve axon terminal releases the acetylcholine. We'll get to the binding with the junctional folds. And what it generates is not, although when we talk about how things move, yeah, nice. I see you once a year. AP2 students. I gave them such a hard time. They didn't go into my micro class. Oh, it didn't fit in my schedule. Read that as you're too hard. I get offended by things like that. What are they getting out 10 minutes early? Did I miss the movie? Never, where was I? Here's the first nugget. That's a distinction between nerve and muscle physiology, the first major event that occurs there. When nerves talk to nerves, it works a little differently than nerve talking to muscle. The action potential, the acetylcholine binding doesn't immediately make the muscle move. It creates a localized potential called an end plate potential. Okay, and it's really a summation of activities. That's what this is. Now, at a muscle, at a neuromuscular junction, the acetylcholine is always going to make the muscle more likely to fire. But it must reach threshold. Unless it reaches threshold, unless there is enough change of ion movement, creating more positivity across the membrane on the interior, that resting membrane potential, if it does not reach threshold value, that will not fire. It will cause nothing really to occur. So effectively, we get a kind of phenomenon called summation. We sum up those effects. So it binds and it causes an end plate potential. You're going to see there's a different type of reference to the same phenomena when nerve kind of talks to nerve, if you will. The local depolarization will trigger an action potential if it reaches threshold. The action potential, once it reaches threshold, means that change has gone far enough to trigger a chain cascading reaction by contacting voltage-gated sodium, then potassium channels. And once it does that in all directions, that's another big difference. Directionality. If the motor end plate, if this is the length of the muscle, the motor end plate is here in that muscle fiber. It goes forwards, it goes backwards, it goes over, it goes under, in all directions. The nerves don't work that way. You say in my old neighborhood. Don't work that way. Nerves are unidirectional. Don't go backwards, they only go forwards when it comes to the electrical discharge. Other phenomena, backwards. Or in both directions. What happens then, if it triggers the action potential, then we'll get to excitation, contraction coupling. We'll get to those T tubules. We'll release the stored calcium. We'll cause the muscle to move. So, summarizing, Action potential at the axon terminal. Voltage gated calcium channels open. Calcium enters. Calcium entry causes release of acetylcholine into the cleft. It diffuses across very rapidly. It's a large volume, very short space. Opening ligand gated channels, sodium in, potassium out. End plate potential. If we didn't have a means to stop the process and reverse it, every time we contracted a muscle, it wouldn't relax. That's what happens when you get a disease called tetanus. Effectively, you have no way to relax. It doesn't come from this particular area, it comes from somewhere else, but we'll get into that in a bit. So when you see that kind of a phenomenon, okay, a spasm, it has to do with the fact that it can't, so we effectively, it's just like when we say blood clotting. Every time blood clots, and it clots all the time, it's like repairing roadways in your body, we have to activate a mechanism to gobble up the clot, or you'd be filled with clots. So this is the mechanism. It involves an enzyme that is in that area called acetylcholinesterase. So there are three methods. We won't get to them today, but I'll start with them next time. So when it comes to that neurotransmitter, the acetylcholine, three ways. It can diffuse away, either totally or partially. It can be metabolized. That's where the acetylcholinesterase comes down, or broken down. Either word, either term word. Or, and this is a very important phenomenon that we talk about a lot down the road, reuptake. When the acetylcholine is broken down into acetic acid and choline, reuptake means the choline is sucked back up and recycled. We're very efficient. We recycle. It's a big thing on our bodies. Shut up, Lou. Nobody cares. They don't think you're funny. We don't have to see you till Friday. Goodbye. Have fun storming a castle. It's been real. Don't like anybody.
Oh,